Hello, this is Carl Kirkconnell from West Coast Solutions. I am very pleased to be presenting to you today our paper on radiation hard cryocooler electronics for hot midwave IR sensors. This work was done in collaboration with Mark Martin, Tim Medina, and Noah Hudson, also all from West Coast Solutions. A little bit of a backdrop here, small sat cryocooler systems today. Small sat missions are all the rage. We're seeing it larger quantities, both commercial, science, and on the military side of things. The Air Force talks a lot about resiliency through disaggregation. And as these small satellites become more proliferated, there's an increasing interest in developing compatible infrared payloads. Unfortunately, the cryocooler system is generally a volume and mass hog on these infrared payloads, never an insignificant factor, and oftentimes with current art, a limiting factor that may even prevent implementation of a particular IR FPA technology. There are, on the tactical side of things, a large number of coolers that have been developed, been presented at this very conference over the last 4 or 5 years. Showing some examples there along the bottom from several providers this type of technology. I apologize if I left you off, but there are a large number of these coolers that are highly relevant to this kind of mission if they can be paired with the proper cryocooler control electronics. Even for limited duration, low Earth orbit type missions, there is still, in most cases, a strong desire on the customer side for radiation hardened solutions. And that's where we're focusing with this present effort. We are trying to develop a set of electronics that is well matched to these very small coolers to enable the implementation of these coolers as a system, as part of a system for these types of small satellite missions. A little bit of prior work, and this is some work that we are pleased to have been a part of at West Coast Solutions. This is a project, a NASA INVEST project called the Hyperspectral Thermal Imager. It's being led by Hawaii Spaceflight Lab and their co-prime Jet Propulsion Lab. And we are indeed, with the current ART technology, implementing a cryocooler on a very small 6U satellite. The cooler in this case needs to go down to about 67 Kelvin. So we're using a small, but not quite as small as some of the coolers of interest for the present effort. And I showed you on the prior chart, but still a small compact cooler, the AIM SF070. We're pairing it with a Cryari MCCETS. This is another collaborative technology, West Coast Solutions and Cryari, and a custom input ripple filter developed for the high-tie payload. So using current art, we are able to package a cryocooler system on a 6U CubeSat, and this system is progressing towards a launch later in 2021. And this solution does support the science. It is a compliant solution, but there are certainly some regrets. This mission is heavily duty cycled. It only operates for about 10 to 12 minutes for maybe 4 or 5 orbits, and then is off for the next 10 or 15 orbits. And this heavy duty cycling is being done to manage the input power and the heat rejection. We have to let the batteries recharge, and we have to make sure that the radiators can cool down. So for this particular program, no problem. But if we're looking ahead to programs of record and systems that need to operate continuously, a smaller, more optimal solution is needed. And it is also worth noting that the cooler is taking up a significant portion of the overall volume on this payload, which could be used for other science. So a new technology is needed. You see the pictures along the bottom there, and I refer you back to the ICC 21 proceedings for a more complete discussion of this work. So our solution, the Compact Cryocooler Control Electronics, CCCE as we are dubbing it. This is a new design. We've done a lot of work at West Coast Solutions and cryocooler electronics, but we in many ways kind of started over. We really looked at every aspect of the design, from the power stages to the telemetry stages. There's additional details provided in the paper that go into that in a little more depth. We did design the system so that we could reuse existing firmware from the MCCE TS line. So that's a big lift, but the hardware is very much different. In this case, it's optimized for the 20 to 25 watt level of output. We can go up above 30 watts. We don't know how far above 30 watts just yet. This is a new development in process, but we're optimizing around that smaller power, lower power range, I should say, because we were really trying to stay focused on the smaller coolers and the 150 Kelvin operation, hot mid-wave IR kind of operating regime. If you'll go back a previous chart and take a look at that MCCE TS, that's about a 100 watt design, and there's some competing radiation hard cooler electronics out there that are about in that size range. But this is substantially smaller. The printed circuit board shown over there on the right, that's actually the brass board that we tested. It is coming in at about 2 inches by 2 inches, and we've done quite a bit of solid modeling. You see some of the results of that down in the bottom left. And we are projecting a 90 gram mass and a 70 cc volume, which is much smaller than any of the radiation hardened cooler electronics that are out there or that have even been talked about in the literature to our knowledge. Most of the work we're going to be showing in here is focusing on testing we performed with two particular coolers, which are underlined here, the SX035 from AIM and the FL100 from FLIR. But it is worth noting that we've tested this set of electronics with other coolers, the prior mentioned 070, and then a couple of the pulse tubes from Lockheed Martin, the Lockheed Micro and the mini pulse tube. And we expect to be presenting some additional work in conjunction with Lockheed in the future on that. But for this paper, we're focusing on the two indicated coolers. So getting into the testing, just some kind of upfront stuff. Most of this paper we're going to be talking about the controls work that we did, but prior to hooking up to a cryocooler, it makes sense to first test with some dummy loads in particular, since these coolers were being provided to us on loan. And I think that loan was contingent upon safe return of the hardware, so we wanted to make sure that we accomplished that here. So we made up a whole bunch of these dummy loads, and you can see the picture over there on the left, and you can see all those coolers that I mentioned earlier. We simulated all of them and did quite a bit of testing at this level, and you can see some of the results of that on the next chart where we talk about some of the efficiency measurements. These setups are very effective for initially just proving out that the firmware could be ported over and showing that the GUI that we developed for the prior system could be readily adapted to the CCCE. And then we can also, once we've verified that the dummy load operations are as predicted and everything's safe, then we can hook up the coolers and start to just take basic functionality and just make sure that we're generating proper voltage and current waveforms. You can see one of the examples, that particular one from the FL100 over there on the bottom right. Prior to getting into the control experiments, we did want to take some efficiency numbers. Now going in, we knew that the efficiency of this brass board was going to be a little bit less than the flight unit. We had to procure this board in a short period of time with a 6-month program window, and we had to use what COTS parts were available. And we already knew that the PFETs had a higher on resistance than what was optimal and than what we had selected for our flight version. But nevertheless, we had predictions for the brass board, and we wanted to correlate experimental results to those predictions to get a better confidence in our projection for the flight system. So we did some measurements. This particular set of measurements was done with the SX035 dummy load. Ran at a couple different bus voltages, pretty low power as you see. Ran it at 15 volt bus, which ends up translating to about 11 watts of input power at max, and 19 volts, which translates to about 17 watts. And I'm showing you the results from that 19 volt case at right. So we measured the tare power. This is the power that the electronics drives before we turn on the motor drives. And I show those values there, 150 and 220 milliwatts of the different bus voltages. Then we hooked this system up through our Yokogawa WT1804 power analyzer. This is a very high precision instrument, so we have a lot of confidence in these numbers, and we calculated the efficiency. So as you can see, once we got above about 60-70%, actually about 60% here, we were at over 90% power conversion efficiency, and this matched up well with the models. Actually, it was a little bit better than the models, which were predicting about 88%. So we're very confident that our 95% expectation for flight is going to be realized once we put the real parts on the board and build it up. So getting into the actual experiments, I know this is an eye chart. This is mostly just for reference, but you can also get this information from the paper. In short, our friends at AIM and our friends at FLIR were kind enough to provide us some loaner coolers, and better than that, they put them in a little integrated doer cooler assembly for us so that we could do operational vacuum testing. And in the case of the AIM cooler, we even had a load heater in there, and you'll see that we got to play with that a little bit. We just performed a very short series of tests here that we're talking about. This is ongoing development, so there's more testing happening, but we thought that these initial test results warranted a discussion here at the SPIE, so here you go. But just a small set of tests. We varied the proportional constant over a couple values and the integral constant over a couple values, and then we played a little bit with the starting point for the loop. This is a very standard PI loop, no surprises there. And this start term just indicates the temperature above the set point at which we initiate the control loop functions. Up to, or down to, I should say, a certain temperature, we just run the electronics at full power. And that's a full power level that's commanded through a register in the firmware. So it could be 100% of the PWM, or it could be 60% or any number in between or below, but we'll just run to that value, and then the system will start controlling once it gets to within a certain range. And so we played with a couple ranges, pretty narrow actually. The 30 ADC, which was the broadest range, kicks in the control loop about 5K above the set point, and the other test results you see were 10 ADC. This is all linear, so it's about 1.7 Kelvin above. We're still playing with that number. I expect we're going to probably end up with maybe like 60 ADC counts for optimal, but that will be cooler dependent and system dependent, and you'll just see some of the initial results here for a particular cooler in a particular configuration. Starting with the SX035, I already described the different values that we varied on the prior chart, so the PI in that start window. And the test setup is shown in the lower left there, so you can see the small West Coast Solutions CCCE over there on the left. It is worth pointing out that on the IDCA that we received from AIM, they also included their off-the-shelf commercial DCE. And if you take a look, our electronics are actually really close in size to that, which is somewhat remarkable given that that's the same size as the board we're going to have for space with radiation hardened components. So as you can see, we really did prioritize size on the design of this board. As far as the test results themselves, they're shown over there on the right. A couple things to explain here. We did a number of different cool downs. In all cases, we started the cool down from above 150K, but sometimes the cool down might have started at room temperature, other times 200 or somewhere in that range. So what we wanted to do to be able to compare the curves relative to each other was we normalized the starting time so that the starting temperature in all cases was about 150 Kelvin. So that's what you're looking over there at the right. And as you can see, all of the curves are pretty well behaved. The one outlier is the gray curve with the lower proportional constant. It has a little bit too much oscillation. You'll see that even a little bit more pronouncedly on the subsequent charts. The start 30 curve does accelerate faster down, but as we talk about in the paper, we think that's really more about thermodynamics and control. There's really no explanation for why that one would cool down faster when the loop doesn't even kick in till 5K above the set point. So we think it has to do with lower rejection temperature for that cooler for that run and a little bit better thermodynamics. So you'll see that discussed in the paper. This is the same data zoomed in a little bit more, and we can draw a few more conclusions from this and see what's going on a little bit better. So in this case, we've normalized the start time, if you will, to 110 Kelvin. So we're zoomed in there, and you can see we get a lot of overshoot with the 4000 P case, both to the down and then to the up when it's recovering back. It eventually does steady out, but we get some undue oscillation. The other curves are all pretty comparable. with the best performance being the one with the highest proportional constant and the highest integral constant. Then we took a look at a step change. So as I mentioned before, we're fortunate to have a load heater on this little test doer. So that was used. We did 100 milliwatt, 200 milliwatt, and 300 milliwatt testing. And I'm just showing the 300 milliwatt here because it's the most interesting. In this, the way that the curve's plotted here, the 300 milliwatts is applied right there at that first time step. And then we just are plotting and how long it takes for the system to recover back to its normal stability, which is right around plus or minus 10 millikelvins. So if you take a look again, the gray curve, the lower P value curve exhibits more oscillation. The other two curves, the orange and the red, have a little bit different characteristics, but essentially the same performance, which shows us that, at least for this particular cooler and this particular set of runs, the ideal coefficients for doing a cool down are the same as the ideal coefficients for handling a sudden step change in the load. And that's not always true for a control system. So this was a fortunate finding. You don't want to have to be hunting around for different P&I coefficients while you're on orbit, but it's something we're going to spend a little bit more time characterizing. Next chart here, the FLIR FL100. So this one got into test a little bit later. Don't have quite as much data to show just yet, but we do have some initial data. We did a number of runs. Again, no surprises. Everything worked quite well. You can see that photo down in the lower left, and again, it's got its control electronics there, and we're not using them. We're using our control electronics over there on the left. So same basic setup as with the AIM SX 035. In this particular case, we didn't play with that start range, but we did vary the P and the I using the same values that we used for the AIM SX 035. Similar results. In this case, the gray curve has a lot more oscillation and it hadn't even steadied out at the end of this window that we were looking at. The two other curves were pretty comparable. The smaller eye seemed to work a little bit better for the FL100, and this isn't surprising. We expect that ideal coefficients are going to be cooler specific. They're going to be system specific, and obviously if you've got a thermal strap and a time lag between your heat load and your cold tip, they're going to be a lot different. So take it all with a grain of salt, but it does show that the curves are performing in an expected kind of way, and we are seeing the sort of dependency on the thermomechanical hardware that we would expect to see. So what's next and where are we? So we are developing this set of electronics. It's coming along quite well, as you can see. We're targeting less than 90 grams, less than 70 cc's to be well matched for these small coolers. The target are these hot midwave infrared space payloads, but there's other applications. Using a number of small coolers on multi-stage systems is of interest, particularly as the coolers and their associated electronics get smaller and smaller. So we expect to be kind of stretched, and we also expect that folks are going to show up who might want a 50-watt version of this because they don't quite want the 100-watt version, want something a little bit different. And the scalings do break down at some point. I don't know exactly where yet, but at some point we do get kicked back up into another class of FET, and we're going to be back to our MCC ETS design. So we'll have to see how that one plays out in the future. But for this present version, we're really trying to stay focused down at that lower power level with the technologies previously described. We've been successful so far in our testing. In our short time on this program, we've already tested with 5 different coolers from 3 different vendors, bracketing both Stirling and pulse tube. No real surprises with any of that testing. The efficiency number of 95% that we expect to hit for the flight model, we're very pleased with that. We would probably actually be pretty pleased with 92, 93% that we saw at the brass board. The very small size of these electronics, these are pretty good numbers. The PI loop work, we spent a good bit of time talking about that. It's behaving predictably. A lot more work to do there. And really what we're going for is to come up with procedures to do very rapid optimization of these loops and information we can provide for customers so they can do this optimization themselves. And maybe we even automate it ultimately. That's a little bit of a further goal down the road. As far as the hardware goes, the very next step is the engineering model design. Now that we've done a brass board that is directly traceable to a flight design, it's very easy to now go back to that flight design, realize it in hardware, and take it through the qualification paces like we've done many times before. And we're looking at a pretty short timeline here. We expect to be TRL 6 in 2022. So we are ready to start even entertaining conversations about flight missions. Not ready to fly just yet, but we will be in that 2022-2023 timeframe. Finally, I'd like to thank some folks here. There was a lot of collaboration that went into this program beyond just the four authors on the cover sheet there. I want to thank Ingo. Thank you, Ingo, for loaning us the SX035 and providing it in the IDCA configuration. Also want to thank Ted and his colleagues at FLIR. Thank you, Ted. The FL100 was a great boon to our testing activities, and we appreciate you loaning us that as well. And finally, want to thank our sponsoring agency, NASA, and in particular the SBIR Program Office, and our technical monitor, Dr. Jeff Chaw, for their financial support and technical support. And Jeff, thank you for the guidance along the way for types of missions and cooler technologies of interest. Very helpful in this kind of development activity. So with that, I'll just close the paper, invite any of you to get a hold of me via email or telephone for any follow-on, and I hope you enjoy the rest of the conference.